Hey, good morning, everybody. So, this is a video set of directions to accompany the directions that are already written down for the activity Energy, Work, and Power. So, we're doing 3 activities this week. This first one is more of an activity than a lab. The second one's more of a lab. The third will be mostly note taking. I'm not sure whether or not I'll just give you the notes or have you look some things up and we'll discuss them. All right, so this activity, Energy, Work, and Power, is the first one you're going to do. This first page is simply some vocabulary you're going to taken right from the notes, the Energy, Work, and Power notes from last week, which I linked to this week again. So you want to go through those notes, make sure you can answer these questions. Easy. Backside, there are 4 activities, and they're silly, but basically, I'm having you practice 2 equations, 2 formulas. The first one calculates work. Now, work is a scientific term, but it talks about moving something around on the surface of the planet here. So it could be your body, it could be air molecules, but you're accomplishing something by moving something physically. And there's a few variables we need. The definition is the use of energy, and so it can look really different in different forms. The formula for calculating work is this. Work equals force times a distance. Now, a force, you know from the notes, or at least that has been introduced to you as a new science concept. We measure forces in newtons. A force is a mass times an acceleration. So actually, to calculate work, you need a mass times an acceleration times distance. The cheesy way I tell students to remember this is pretend you don't like work, and it makes you mad. So to calculate work, you need to have these 3 variables, and you just multiply them by each other. There should be a little multiply right there. All right, so you're going to take work, multiply, to calculate work, you're going to multiply the mass. This has to be in metric, so we're talking kilograms, times an acceleration, times a distance. This has to be in metric, so we're talking meters. If it's half a meter, it's 0.5 meters, so not centimeters. Now, you need to get these these quantities at home, so you can just measure something or say, oh, that's about 10 pounds, or use your own body weight and say, okay, I weigh about 100 and whatever pounds, and then get online and say, okay, pounds to kilograms, and have this now measured metrics for you. Just convert it, and it's really easy to do even without math if you just go to a website online that does that for you. Similarly, you can then convert something that is in inches or feet or miles and convert it into meters for a distance. So all you need to do is calculate work 4 times. I came up with some ridiculous exercises for you. The first one says physics is heavier than it looks, and have you take 2 textbooks and lift them with your arm straight down to your arm straight over your head and do it like 10 times. So you look ridiculous. And these silly little things, I said each one weighed 1 kilogram, so you're moving 2 kilograms. After 10 times, it gets kind of tiring, which is also silly and embarrassing, but your little muscles get like, whoa, this is a lot of work. So I want you to calculate how much work it is. So how much did the books weigh? I said our textbooks weighed 1 kilogram each, total of 2 kilograms. What's the distance? And measure your arm straight down to straight up in the air, and how far is that book going to move? It's going to travel each time you do it. You'd have to then multiply that by 10. Let's say you did it 5 times. You'd have to multiply it by 5. What's your total distance? So it's what you measured times the number of repetitions you have. Okay, so now you can calculate this formula. What you need to know about this formula, every single time you do it, in this exercise, and in maybe most of the applications we'll use all year long when we're calculating this kind of stuff, the acceleration won't be how fast you're moving the book, as in this example, but the strength of the Earth's gravity. So you could calculate the amount of work you use if you pushed a car that was broken down. You had to move it a block because it was out of gas, and that's where the gas station was. You could calculate how much work that was, but it would be a lot easier to do if you're on the moon where gravity was weaker. You could calculate how much work you did if you lifted a 100-pound weight, but it would be a lot easier to do if you did it on the moon where where the gravity is weaker. So this acceleration isn't how fast you're actually moving, it's the strength of the acceleration of gravity. So, important to note, easy to get confused. As you know from the notes, because you have a photographic memory and you read them once and you remember everything, acceleration of gravity is 10 meters per second squared. It's actually 9.81 meters per second squared, and throughout the entire semester, every time you do a calculation for me, you can round that up and makes your math really easy. So the acceleration of gravity that we'll use in class for our calculations is 10 meters per second squared. And so in these math problems, we have to calculate work. The way to remember this is the formula is MAD, mass times acceleration times distance. This number will always be the same. So you really only need these two variables. How heavy is this object? How far did you move it? And then you can multiply it times the acceleration of gravity and calculate the work. The units for work will always be in joules. So it's dumb, bad dad joke, cheese ball, way I tell students to remember that is, first of all, oh man, I hate work. The formula for the calculation of work is MAD, mass times acceleration times distance. And then when you finally do this work you've been avoiding, you get paid for it. And how does the queen pay you? In joules. Instead of getting cash, you get a bunch of diamonds and rubies. We measure work in joules. So, let's see here. That's how you spell the word joules. You should know it from the notes. Let's just make up a math problem. Let's say that you want to calculate work. You took 4 kilograms, hopefully you can see that, times the acceleration of Earth's gravity, 10 meters per second squared, times a distance of 2 meters. If you multiplied those things together, 4 times 10 is 40, times 2 is 80, you'd have a total of 80 joules, capital J. Ook. That is the simple formula. You're going to practice it 4 times with our ridiculous activity. Now, once you've completed that formula for an activity, you then calculate the power. Formula for power is the work you just identified divided by the number of seconds it took you, divided by time. So, for example, if I've got to push a car, a block, let's say that's 100 meters. To the gas station, and it takes a certain amount of force, and I get it going. I'm doing that on the Earth's surface, so I'm concerned with the acceleration of Earth's gravity. And then I go a certain distance, 100 meters, that's a certain amount of work. And if somebody was 400-pound, incredibly fit, 28-year-old NFL football player were to do the same thing, it would be the same exact amount of work because the car weighs the same, and the 100 meters is still 100 meters. Strength of Earth's gravity hasn't changed, right? So all those variables, MAD, are the same. Mass, acceleration, distance. What might be different is that football player might do it 5 times faster than me because he or she would be stronger than I am. So they're demonstrating more power. They're doing the same amount of work but in less time. So if you think about it in the gym, I'm going lifting weights. I haven't been there for a while, and I'm going to bench press, and I'm the guy everyone's kind of trying not to stare at because they're really concerned I'm going to die as my legs are kind of up in the air and I can barely get it off of my throat for a while, and it's kind of touch and go for half a minute, 30 seconds. Everyone's wondering, oh my God, do I have to go rescue that guy? And I finally get it up. Okay, I lifted my 95 pounds once. The NFL football player comes in and then lifts that as a warm-up and does it 20 times. And each rep takes like 1 second. Really fast? Okay. Now let's say that we just take their first rep. All right. Same work. The bar weight's the same. The weights are the same. Total mass, 95 pounds, whatever that's in kilograms, the same. Let's say his or her arms are the same length. So the distance you're lifting the bar is the same every time. The work is the same, but they did it in 1 second. It took me 30. They are more powerful because they could do it in less time. So the formula for power is work divided by time. You've got these 4 exercises to do, and for each one you'll calculate the work. Time yourself when you're doing it. for the second calculation, to calculate power, you're going to then divide that by however many seconds it took. So the last calculation we did, we said power equaled, and we said that, and that, I don't remember what we said we were lifting, but here you calculated 80 joules of work. Let's say now that that took 4 seconds to do it. So your power then would equal 80 divided by 4, super easy math in my example here, 20. The units for power are watts. Watts is a rate. Same thing in a light bulb. 100-watt light bulb's more powerful than a 20-watt light bulb. It puts out the same amount of light, but it puts it out a lot faster. It's doing the same amount of work in a much shorter time. And we can talk about power with things like horsepower. There are other units, but in metrics we use watts. So you're going to do those 4 calculations really easy. I want you to be kind of familiar with them. We're going to then do the second lab this week. Will be on efficiency. We're going to use an electrical device, a heater, and calculate the amount of power and work and such, but then see how efficient it is, the amount of energy in versus the energy out, kind of like when we did the energy transformation game. So we're talking about an electronic device that changes electricity into thermal energy, and we're going to see how efficient it is, how much of that energy is wasted, how much goes right into making the water hot for tea. The reason we're doing both these things is ultimately we're going to be talking about pulleys and simple machines, and you're going to have to calculate their mechanical advantage, and so you'll need to know some of these variables, and you'll need to then calculate their efficiency. So we're just introducing those concepts with these little activities. At home, if you can't do the things described here, like running up and down the stairs, you really have to stay at home and there are no stairs. You can do something else. You can do a push-up or a pull-up, and you can use your body mass, whatever you weigh and what you think you weigh, turn it into kilograms, figure out the distance you moved, and just use that activity. If you want to come up with something else, you're going to take a gallon of milk. 1 gallon is about 8 pounds, and you're going to lift it. Great. Get the total distance you moved it, convert its mass into, well, both those quantities into metrics. And show me your work. I really want to see these 4 problems. There's some questions to answer. Get that sucker done. I'm going to post some more directions soon for the Let's Make Tea activity, but there are written ones there if you want to go ahead. I got to get to class. Have a good one, and talk to you hopefully on Thursday. Bye.